Hello, a Rosie math teacher coming at you from my 6th period accelerated grade 7 math class. Today we're working on the last lesson in module 1, y'all. Here we go. Lesson 1-10, compute with scientific notation. Today we are working pages 85 to 86, items numbered 1 through 10. So don't forget, you're going to need to turn that page. But let's begin with item number 1. There are about 3 times 10 to the 11th stars in our galaxy. Class, please draw a box around or circle 3 times 10 to the 11th stars in our galaxy. And about 100 billion galaxies, please circle that information, 100 billion galaxies in the observable universe. Wonder what they're going to ask us to do. Suppose every galaxy has as many stars as ours. How many stars are in the entire observable universe? Write in scientific notation. So class, will they want your answer in standard form? Yes or no? No. They want your answer in scientific notation form. Now, I'm about to show you something that I hope you've already learned before. Don't copy what I'm writing, just look up here and listen and understand what I am explaining. Do you recall learning long, long ago, hopefully when you were in elementary school, do you recall learning that 1/2 is equivalent to 2/4? Wave if you remember learning this. Okay, now the second question. I don't know if any teacher has ever taught you this, hopefully they have. Have they ever taught you how when I cross multiply 2 fractions that are equivalent, I will get the same product in both parts of my x? Wave if you have learned this before. Okay, let's go ahead and practice on my 1/2 equaling 2/4. Class, what does 2 times 2 equal? 4. What does 1 times 4 equal? 4. Can we all agree? Those are the same product. Yes, and a product is an answer that we get when we are what 2 numbers? Multiplying. What are those 2 numbers called? Factors. That was just extra practice for you. Factors. Okay, so now that we have established what we can do with fractions, can we also agree that ratios are similar to fractions in the way they can be set up? Are you familiar with a ratio looking like this? 4 out of 5 dentists recommend Crest. What does that mean? It means 4/5 of all their patients prefer the toothpaste they're advertising. Might be true, might not. Who really cares? My point is this. A fraction can also represent a ratio. And a ratio can also represent this many out of this many. I'll show you what I'm hinting at in just a moment. So you're going to use those 2 pieces that I just described to help you understand how to set this problem up for success. Ready? Watch. I want you to create a ratio that shows the relationship between the number of stars to the number of galaxies. And you may just abbreviate galaxy or galaxies, GAL. So let's use the information they give us in the beginning of item number 1. There are about 3 times 10 to the 11 stars. Where shall I write this number? Numerator or denominator? Say it. Numerator. Class, please write 3 times 10 to the 11 stars. And my 11 looks super sloppy, so I'm going to fix that and move that S over just a little bit. 3 times 10 to the 11 stars. Have you copied this so far? I do want you copying this. 3 times 10 to the 11 stars over top of blank galaxies. Now it says in our galaxy. So how many galaxy?
100 billion.
How many galaxy? 1. As soon as it is a singular form of the noun galaxy, you therefore know that our galaxy is only 1 galaxy. What galaxy do we live in, guys?
The Milky Way.
The Milky Way. You got it. Glad you're listening in science class as well as math class. Now that we have this ratio, that there are 3 times 10 to the 11th number of stars per how many galaxy, class? 1. We can use this to help us discover the answer to the question, because what did they ask? How many stars are in the observable universe if the observable universe contains 100 billion galaxies. So at this point, I'm going to teach you a song. Are you ready? It goes like this. I'm unstoppable with ratios and proportions. I write down what I know and what I want to find. What do I want to find? I want to find how many stars are in the observable universe. I write down what I know and what I want to find. I write my labels down. I keep same across from same. See, stars across from stars, galaxies across from galaxies. And then I'm going to cross multiply and divide by lonely number. Here we go. How many galaxies did they give you in the word problem today? Read the number to me now. Say it, class.
100 billion.
100 billion. Before we go any further, because I would like you to write that in scientific notation form, because what did they ask for the answer in? Scientific notation form. So we want to use that for the number of galaxies. Let's first write it in standard form and then convert. So, tell me if I have written the number correctly yet. It's 100 billion. Would my standard form number look like this?
No.
No. How about if I go comma, triple, zero? Is that finished?
No.
No. What is that?
100,000.
100,000. How about if I add on another set of triple zeros?
No.
What is that?
1 million.
100 million. How about if I add on another set of triple zeros?
That's 100 billion.
That is 100 billion. Class, I need to change this to scientific notation. Where do you think I want to place my new decimal? Immediately after the what?
The 1.
The 1. Remember, scientific notation always begins with a single digit, and then a decimal beside it, and then times 10 to the whatever power. Now wait, do we need this digit if it's the whole number 1? No, we do not. So get rid of that decimal. We do need the digit. We don't need the decimal. That's what I meant to say. All right, please draw brackets around your standard form number so that you can figure out how many powers of 10 you're multiplying by. Where does my first bracket go? Say it if you know. After the, in the standard form, after the 1. Where does my ending bracket go? At the end of the number. You got it, guys. Great job. And now, how will I determine the number of powers of 10? How will I find that exponent? Yes, ma'am.
You'll count how many zeros.
I'll count how many spaces there are between the brackets and go ahead and tell me.
11.
11. So class, do you understand why this would be equivalent to 1 times 10 to the 11th power? All right, now since it's 1 times 10 to the 11th, do we really even need 1? No, we don't. So go back to your empty space in front of galaxies and please write 10 to the what? 11th power. Now we are ready to cross multiply. Oh, now I have to finish singing the whole song. It goes like this. I'm unstoppable with ratios and proportions. I write down what I know, including this, and what I want to find. I write my labels down. I keep same across from same. Then cross multiply. Class, draw yourself a cross multiply circle situation. Then divide by lonely number. I'll do that better next time. And then you will find the final amount of stars per 10 to the 11th galaxies. So let's multiply. 3 times 10 to the 11th times 10 to the 11th. Write this somewhere that you have white space in your life, not underneath number 3. Please write 3 times 10 to the 11th times 10 to the 11th. Guys, it's not as hard as it may at first appear, and I'm tracing over it with bigger, bolder ink. Can we all see my writing? Oh yes, now we can. Now that you see we are multiplying 3 times 10 to the 11th times 10 to the 11th, what do we remember about when multiplying same bases? You add the exponents. So recopy this as 3 times what?
10, 11, or 10.
10 to the,
11.
well, are we multiplying same bases here, guys?
22nd.
So to the 22nd power. Class, do you understand why this would be equivalent to 3 times 10 to the 22nd power? Yes. And then I divide by my lonely number 1. Hey, is that going to change my value at all? No. So what is the actual answer to item number 1? Read it, please. 3 times 10 to the power of 22. Wait if you understand. Raise your hand if you have a question. You're not quite getting it. Yes.
On the calculator, it did it for a couple, like whenever I was doing computer.
Uh-huh.
But it keeps on, like, it didn't say, the 10, or 3 times 10 to the 22nd power.
Uh-huh.
It just keeps on giving me, like, a number and then to the something.
Yes. You don't want to use your calculator for this.
Okay.
You want to use just your brain power
What you know.
of knowing. I got my assistant teacher back there. Are you here? Okay. Of what you know about when you multiply 10 to the 11th times 10 to the 11th. You want to do the thing where I'm multiplying same basis, so I'm going to add the exponents. So thank you for asking that question.
And then, I also had a question, because it was with the calculator as well.
Uh-huh.
It had, like, I put it in, like, how I had it on the paper.
Okay.
And it told me it was wrong, and so then I put it into the calculator, and it was giving me the same thing.
Okay. So we'll probably talk about that a little bit after class.
Okay.
Okay. Definitely ask me again. All right. Do I have any questions on number 1? Any further questions on number 1? All right. Let's go to item number 2, guys. Number 2. Humpback whales are known to weigh as much as 80,000 pounds. Oh, you wouldn't want that dude to sit on you, would you? The tiny krill they eat weigh only 2.1875 times 10 to the negative 3 pound. About how many times greater is the weight of the whale? All right, guys, when we're doing how many times greater, do we recall what we're going to create for this situation? Do you remember my story when I was growing up in Maine and I would be at the top of a large mound of snow and we would play the game King of the Mountain? All right, who ends up as king or queen of the mountain?
Bigger one.
The bigger kids. I wasn't a bigger kid. I was a smaller kid. So the bigger kid would shove me down to the end of the mountain, the bottom of the mountain, boom, 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 face plant in the snow. So, yeah, we made the glasses fall off. Or break. Anyway, so at the bottom of the hill goes the little people. Okay, so we're going to do that with this problem. It will help us tell about how many times greater is the weight of the humpback whale. But wait, they use the word about. So do we want to use perfect, precise numbers or approximate numbers? Approximate. Guys, on the 80,000 pounds, do we really need to round that? No. It's already got a significant digit that we don't need to change. So let us write the weight of the whale in scientific notation form. Will the whale, compared to the krill, will the whale be king of the mountain or at the bottom of the hill?
The king of the mountain.
The king of the mountain, thank you. I was expecting everybody to say that. All right, so draw a fraction bar, otherwise known as the mountain. And on top of the mountain, we're going to write the scientific notation form for the whale's weight in pounds. So looking at 80,000, class, remember, we're going to begin this number with the significant digit of what? 8. Will we need to keep this decimal, yes or no?
Yes.
No, we won't. But do we need to draw brackets up above where the 8 ended?
Yeah.
Yes. Let me get rid of my other writing about it so there's nothing distracting your eye. And on the TV screen, I hope you can see that I have rewritten the number 80,000. We are going to start with a bracket where the decimal would be if we were writing it. It's a whole number. That's the only reason we don't need to write it. And then place our last bracket at the end of 80,000. So now we know we're doing times 10 to the what power? Listen to the hands. Think, think, think.
4.
4th power. Love your answer. Where does that whale's weight get written? At the top of the hill. The whale is the king of the hill. Do we follow so far? Now, the weight of the krill. What happens when the whale shoves the poor little krill to the bottom of the hill?
He falls.
Face plant in the snow. So, the krill's weight needs to go here. Also in scientific notation form, but wait! Also, we need to do about. If the word says find about, Do we want a precise amount or an approximate amount? Approximate. When it says about, we want approximate. So let's go to this number, 2.1875. Let us round it to the nearest whole number. So let's only look at 2.1. Underline the 2. Draw your arrow to the right. Looking at my digit to the right, is it a 0 or 1, 2, 3, 4? Keep the same number on your rounding floor. Is it a 5 or 6, 7, 8, 9? Add one more number to your rounding line. Will you keep the same number on your rounding line, or will you add one more number, class? Keep the same number. So now we are writing underneath that line, that fraction bar line, 2 times 10 to the what?
The negative third.
10 to the negative third. Now, when you look at this, you might think, there, I'm all finished. No, not so fast. I also do not want you plugging this into your calculator because I want you to know how to say it in scientific notation form. And then we'll go from there. Hold on, wait for it. I want you all to put a box around the matching style of numbers. For example, are these both number values, standard number values, the 8 and the 2?
Yeah.
Yes. Draw a box around them right now, please. And when you look at the fraction bar between them, what operation does that mean? Add, subtract, multiply, or divide? It means divide. So read to me and say the answer that you know I'm going to write below this. 8 divided by 2 equals?
4.
Not a trick question. Good job. 4. Copy your multiplication symbol and then ask yourself, where else shall I draw a box? Around my base values that are both what? Tens. Now remember, when dividing same bases, not multiplying, when dividing same bases, what sign is in the middle of a division sign? Subtract. So in your calculator right now, tap the first number in that ratio, then tap your what key? 4 is not negative, so we're just going to tap 4 and then tap what? Minus. Love your answer. And then tap what? 3 with a positive negative. Love it. So 3 with a positive negative equaling, ready, go.
7.
Correct. So 3 times 10 to the what power? 7. Class, if you saw this question on a test, I would want you to know how to recognize this answer in scientific notation form and also how to recognize it in what form? Standard form. Do not use your calculator to try to get standard form for this. The whole purpose of scientific notation is that you learn how to go forward with it, backward, forward, backward. You should be able to translate scientific notation to standard form, standard notation to scientific notation. So let's convert this one right now. Please rewrite just the 4. Place the decimal where you know it belongs. Where does the decimal belong? In front or behind? Behind. Oops, right there. There's where it is currently. But then it says times 10 to the 7th power. Class, is that exponentially increasing value or exponentially decreasing value? Increasing. So which way will I scoop the decimal to make the number increase? Okay, I have a variety of answers. The correct answer is to the right. Wave at me if you said to the right. Okay, when I scoop the decimal to the right, I will be increasing the value exponentially. Now, how many times will I scoop that decimal to the right? Say it. 7. Beautifully done. 1, 2, 3, 4, 5, 6, 7. Guys, make neat buckets or you're going to accidentally do too many zeros. Fill in all your empty buckets with a 0. Then go back and place a comma wherever you think it belongs. Read your answer to me now. Ready, set, go. 40. 40 million is correct. Wave at me if you understand how to go either direction. Okay, do I have a question on how to convert from standard to scientific or vice versa? All right, so let's head on to item number 3. Guys, item number 3 is a little bit tricky, kind of like the homework last night was, where you wanted to convert all of the bases to where they had the same exponents. Do you know what I'm talking about? Okay, you're going to do the same type of thing here. In number 3, in the first set of numbers, I have, and this is too big, I have 1.28 times 10 to the 5th power plus, and then they have 1.13 times 10 to the 3rd power. When you see that you are adding them, here's what you're trying to do. I'll explain. You're trying to get these factors to be exactly the same so that you only have to add these values. But we can't do that yet because are these factors the same as each other? No. Now, do not write this to the side, but please stop what you are doing and look up for a moment while I just use some empty white space to remind you of something you've known since you were, well, remember when you were one of those cute little bitty 6th graders at school? Yeah, you've known it since way before that. Okay, watch. Are you familiar with the fact that if I did 20 times 100, I would get 2,000? Yes? Okay. Hopefully you learned this long, long ago in elementary school. Not even kidding. I taught it in elementary school. If I divide my 100 by 10 and multiply my 20 by the same amount, class, will I still get 2,000?
Yeah.
Yes. Yes, I will. The rule of math states when multiplying one factor by a power of 10, also divide the other factor by that same power, and you will get the same product. So watch. What is 100 divided by 10? You know it. Say it. It is 10. What is 20 times 10? You know it. Say it. 200. Class, do you agree that 200 times 10 also equals 2,000?
Yeah.
Yes. Now that you've refreshed your memory about this, wait, let's try it another way. What if instead I were doing, let me clear that whole page. What if instead I were doing, oh, I don't know, let's say that I did 100 times 50. What would that equal? It would equal 5,000. Copy the 1 times 5, copy the 3 powers of 10, so 5,000. Do you see how that would be 5,000? Now what if this time I divided by 100 instead of, now earlier, did I divide or multiply earlier? I multiplied, okay. So I want to divide by 100 this time, not even just by 10, I want to divide by 100. If I divide 100 by 100, what would I get, class?
0.
No, I would get 1. 100 divided by itself would equal 1. So if I divide this by 100, what do I now need to do over here? Multiply by 100. It doesn't matter how many powers of 10, as long as you do the same number of powers of 10 to both sides and you do the inverse operation. What's 50 times 100? It is 5,000. So would 1 times 5,000 still equal 5,000? My point here is this. If you are dividing by a power of 10, the other factor needs to multiply by a power of 10. If you are multiplying by a power of 10, the other factor needs to what? Divide by the power of 10. And whatever the number of powers of 10, you have to use the same powers of 10. So let's go back to our situation for item number 5. And now I'm sad that I let the example go away. Okay, 1.28 times 10 to the 5th plus 1.13 times 10 to the 3rd. Class, I want to make these match. I don't know about you, but I prefer taking the lower one and increasing it to match the higher one. So let's do that, just because I'm in the mood for that. So I want to convert this 3 and make it a 5. How many powers of 10 do I need to multiply by to bring the level of 3 up to the power of 5. Say it, class. 2 powers of 10. What is that number?
20.
No, 2 powers of 10 are not 20.
Oh,
Try again.
100.
100. So if I multiply 10 to the third times 100, am I right? I would now have 10 to the fifth. Yes or no?
Yeah.
Yes. Since I multiplied this factor times 100, what must I do to this factor so they will still equal the same product? Divide it by 100. Remember, do the inverse operation, but same value. So when you do 1.13 divided by 100, which way will this lovely decimal have to scoop to make it divided by?
Left.
To the left. How many scoops?
102.
2 powers. Because we reduced it by 2 powers of 10. Do you get how you will now see